Okay, thank you. Okay, good morning, everybody. I hope you're enjoying OCX so far. My name is Laura. I'm from the Mercedes-Benz Tech Innovation, and I hope you will enjoy the OCX even more after my talk. My today's topic is enhancing the software supply chain approaches to software composition analysis. So what you can expect today. So first of all, I will give you a short introduction to the software supply chain security. Afterwards, a short introduction to software composition analysis. Then I will give you some motivation or why we at Mercedes-Benz Tech Innovation like to deal with this topic or why we investigate this topic. I will present my methodology, how we evaluated the FOSS tools. And of course, I will give you a short conclusion afterwards. First of all, who are we? We are Mercedes-Benz Tech Innovation. We are 100% subsidiary and exclusively working for Mercedes-Benz. And this for over 25 years. So we're producing software for over 25 years. Of course, not me, since I'm a little bit younger. Our CEO is Daniel Geisel, our CFO, Christine Luckert. And our headquarters is in Ulm and in Stuttgart, but we are also located all around the world, Spain, Malaysia, India, and Turkey. So we will start with the introduction to the software supply chain. Basically, the software supply chain is everything that belongs into your software package. So everything from the source code, from the producer to your build, to the package you deliver to your customers. And today we want to look especially at one part, at third-party dependencies, which are basically in every software build. Like it has a lot of advantages, speed, reproducibility, and so on. But also third-party dependencies bring some risk with it. And just to name some examples, maybe you heard of these attacks of the supply chain, attacks and vulnerabilities. Actually, there was the data breach of Equifax. Equifax is kind of like the German Schufa, so if the data is or gets spreaded, it's not that good. Then you heard of SolarWinds, which actually results in the executive order from the White House. So software delivered to the White House is required to come with the software bill of materials. And maybe you also heard of the Apache Log4j vulnerability in 2021, which almost affected every big company and kind of sets the internet on fire. So the question is not, do I really need this, or do I really need to track my third-party dependencies? But the question is, when will be the next big issue with third-party dependencies? Now I give you a short introduction to software composition analysis. So let's imagine we have built some software running on any background, maybe some Java software on a loading station for electric vehicles. And we have two components, or two dependencies, a dependency A and a dependency B. And we can control them, right? We know which version is in our software. We know which dependency we actually use. But then it gets a little bit more complicated, since this dependency also have dependencies, transitive dependencies. And here, we cannot really control these transitive dependencies, right? So what happens if a transitive dependency of our dependency, for example, gets a vulnerability, or there is a vulnerability detected? Well, let's imagine our dependencies inherits this vulnerability from the transitive dependency, and we inherit the vulnerability from our dependency. And what's happening now, we are actually vulnerable to this vulnerability. And since this vulnerability are exposed on the NVD, or listed on the NVD, potential attacker can look for this vulnerability, look, okay, it's in maybe dependency D, and look for it where dependency D is used, and then can exploit the vulnerability. And we basically don't really can control it. And that's why we need software composition analysis. So what can software composition analysis do for us? Well, we have our source code, we have our direct and transitive dependencies, And software composition analysis will analyze our dependencies for vulnerabilities and generate a report with the components and the vulnerabilities that belong to these components. Of course, this is kind of related to software bill of materials, but the difference is that we are looking for the vulnerabilities, not directly for the components and its licenses. Now, I come to the motivation. Well, one motivation is clear. We don't want to be vulnerable to third-party dependencies or third-party vulnerabilities. But we from Mercedes-Benz Tech Innovation, our motivation is to secure the software supply chain for automotive software. And also there are kind of two different approaches to do automated software composition analysis. One is the metadata-based approach, and the other one is the code-centric approach. And since software composition analysis is not such a, or does not have a long history, there are kind of problems that it has to deal with. First of all, the vulnerability database, then the metadata approach. Metadata is often incomplete, and of course, both approaches are language dependent. We first take a look at the graphic on the right side. So this is from the insight from our GitHub Enterprise at Mercedes-Benz Tech Innovation. So if we take a look here, we can see it explains the lines of code in our GitHub Enterprise, and we can see we have a lot of HTML code, which is the pink line up here. We have a lot of C code, and we have constantly growing Java code. So we want to explore this field for Java code. And there are currently two FOSS SCR tools, OWASP Dependency-Check, which works on a metadata basis, and Eclipse Steady, that works on a code-centric approach. And as it works on a code-centric approach, it has an additional ability to do a research analysis for vulnerable code. So I refer to this as AS-REACH, just to explain. Both tools can scan Java code, which is important for us. And we wanted to investigate, well, which of these two approaches, of which of the both tools actually delivers more or produces a better quality scan result. And also, we would like to know if this reachability analysis can really reduce the number of false positives, since this is a big problem. Let's take a quick look at the metadata-based approach. So we have here the OWASP Dependency-Check scan engine, and we first scan our files. Scanning our files means we're looking for example, in Java code for POM XML, for Gradle files, and so on. And we scan them for evidence. Evidence can be anything like description for a library and the version. Then we deliver this evidence to the analyzer that compares the NVD, or a local mirror of the NVD, with the CPE, the Common Platform Enumeration, and it looks for matches. And when it finds a match, it results them or generates a report with the results. The code-centric approach is a little bit more complex, so I will not go too much into detail right now, but just to explain how it works. The code-centric approach works on code construct. That means it builds code constructs out of our code and out of the library we're using. And up on this construct, it builds an abstract syntax tree. And in the database of the Eclipse Steady, there's not the vulnerability data, but rather there are fixed commits. So it can look up in this intersection, like the number of fixed commits that overlap with our code constructs from the library, and compares the abstract syntax tree if it's still the vulnerable one or the fixed syntax tree. And therefore, it can detect, okay, we're still using a vulnerable version or a fixed version. On the right side, we can see how the reachability analysis works. So basically, we're first doing a dynamic approach and collect the traces of the dynamic approach. And then we build upon a static analysis on the dynamic approach. And again, the overlap here, these are our reachable or potentially reachable code constructs. Now, how can we compare the two tools, or what was our approach to compare these two tools? Well, we did two experiments. In the first experiments, we analyzed 15 proof of concept projects with basically one vulnerability per project. that we knew in advance, of course. And in the second experiment, we used real FOSS projects from GitHub, also at a time where one vulnerability or one third-party vulnerability was present in the project. Then we scanned the project with both tools, and we compared the results afterwards. And now I'm coming to the results. So we can see here on the right side, this was from the proof of concept project, and we could see that OWASP Dependency-Check basically detects all 15 vulnerabilities in the proof of concept projects. OWASP Eclipse Steady detected 10 out of 15 vulnerabilities out of this project, which is quite still good. For the FOSS project, it looks a little bit different. So we can see OWASP Dependency-Check detects 6 out of 10 vulnerabilities, and Eclipse Steady none of the vulnerabilities. I move on to the next slides, which we should all look at and think, what's happening here? Because two tools doing the same thing, but result in completely different diagrams. As you can see here, we first take a look at the left side. So we can see here, OWASP Dependency-Check results in a quite larger number of detected vulnerabilities. And we can see here the intersection is relatively small. So why? And if you take a look at the reachability analysis, which is here, we can see that almost all non-reachable vulnerabilities are here in the Eclipse Steady only area. If we take a look at the FOSS, or it should be FOSS, not FOSS, the FOSS experiment, we can see almost the same. Like OWASP Dependency-Check again detected way more vulnerabilities than Eclipse Steady, and the intersection is relatively small compared to the whole number. And of course, we wanted to know why. Why differ these tools so much from each other? So we did a manually code review on the proof of concept projects, and we investigated 36 of the total vulnerabilities on a pseudo-randomized subset. We found that actually only 5 of these 36 vulnerabilities were true positive or could be true positives. From this 5, 3 were actually detected by both tools, the other 2 only by OWASP Dependency-Check. We also found that OWASP Dependency-Check has this high number of false positives since it is missing the information of application context. Yeah, exactly. So it does, if there's like, the vulnerability is only exploitable with a certain configuration, OWASP Dependency-Check won't notice. And the false positive of Eclipse Steady comes off a failed version matching, which means it actually detected the correct version of the library used, but it delivers vulnerabilities that belongs to an older version of this library. And the false negatives, like we noticed from the graphic before, that Eclipse Steady could not detect all the vulnerabilities that OWASP Dependency-Check does. And this results because Eclipse Steady's database is missing the vulnerability information. Okay, where is no information, there cannot be anything detected. We also did the quick code review, or quick is good to say because code reviews are very with much effort. We did a manual investigation of the Eclipse Steady vulnerabilities and the Eclipse Steady reachability analysis. Again, we had the pseudo-randomized subset of 12 vulnerabilities, and we actually found that all were false positives, 10 of them, again, because of this failed version matching that I mentioned before, and the other 2 because non-exploitable configurations. And the 2 that were actually because of non-exploitable configurations are also were also found by OWASP Dependency-Check. So this was a lot of information now. So I'm moving on to the key findings. So what are now the key findings? Yeah, first of all, we noticed, okay, OWASP Dependency-Check can deliver way more true positive than Eclipse Steady does, and this is because of the database. Then we found that most of the manually identified vulnerabilities, or the true positives, were actually in the section of both of the tools, means that are detected by both tools. We also could see that the Eclipse reachability analysis marked most vulnerabilities as unreachable out of the Eclipse Steady only part, not of the intersection. And we found that the differences of the findings were actually because of the missing information in the Eclipse Steady vulnerability database and because of this wrong version matching or because of the failed version matching. We also did some research on the dependencies. There we found that actually both tools could resolve exactly the same dependencies. And based on our manual analysis, we also found that actually both tools had a very high number of false positives. This brings us to our conclusion. We notice the quality of the vulnerability database is crucial for correct finding and correct detection. We found that the metadata-based approach of the OWASP Dependency-Check was less prone to false negatives. And we also found that the code-centric software composition analysis approach could actually reduce the number of false positives. And this brings us to the solution that maybe a hybrid approach would be the best solution. We cannot tell, okay, vulnerabilities up in this area are really vulnerabilities, but we can tell with a certain certainty that it might be that vulnerabilities that are located in here are more likely to be true positives than the other ones. So what we mean by that? Well, we first put a metadata approach on the subset. So we have this big subset of vulnerabilities that are found by the metadata approach. Then we put a code-centric approach in it. So maybe the vulnerability found is more here. So it's more likely a vulnerability to be a true positive if it's located here than out here. And on top of that, we can do a reachability analysis to tell, okay, vulnerabilities located in this subset are more likely to be a true positive, and developers should start with looking at vulnerabilities located here rather than starting with vulnerabilities located outside here. Still, this brings some future work with it. And of course, our investigation had some limitations. For example, we could still investigate even more Java projects. Then it should also be, or we should also explore other programming languages, for example, Python. Eclipse Steady also works for Python code. Or like C++ code, which is actually very hard to do on that. Then examining further SCR tools, like there are a lot of software composition analysis tools rise during the last few years, also software bill of material generators, and you can also put or do software composition analysis on top of your SBOM, for example, with OWASP Dependency-Check or tools like that. And also one topic is examining software composition analysis tools, for example, for binaries, like Docker images or stuff like that. Yeah, and I think I'm rather good in time. So this brings me to my mostly last slide. Minimize the risk, what you can do now. So first of all, everyone or every developer should keep track of your dependencies. So you should generate regularly software bill of materials or know basically what's in your software. And not only your direct dependencies, also your transitive dependencies. Second, that's what is the second. Keep track of your direct and transitive dependencies. So yeah, you should also know what's coming into your software from your direct dependencies. And third, keep track of new vulnerability detections, because you might have your SBOM you generated regularly and you looked up the vulnerabilities and you say, oh, there's no vulnerability now, but what if there gets a vulnerability newly detected? Yeah, the first part was keep your dependencies up to date. It's important because normally dependencies patch their vulnerabilities, so you always have the newest version and you always have the vulnerabilities fixed. And last but not least, we are hiring. So if there are any jobs, feel free to join us, or if any friends of you are looking for a job, feel free to join us. And thank you very much. And I'm now open for questions. Yes. I think the microphone is coming.
Thank you for your presentation. I'm wondering what are your recommendations for the vulnerability databases? Because we know that NVD doesn't have any information about the options in the specific software that are affected by the vulnerability. The CV data doesn't have it, neither. So can we fix the situation by augmenting the database itself?
That is an interesting question. Yes, the database is one big problem, and I'm not sure if there is any database that actually gather all the data that you needed, because different STR approaches need different data. So I'm not sure. I don't think that the database only is the problem, and you can solve any problem with the database. I'm not sure if I can answer your question, actually.
Hi. My question is, when you were explaining about using a combination of both the approaches, sounded like an intersection of the findings, but wouldn't that be leaving out the false negatives?
Yeah. The point is that actually both tools are more, yeah, of course, if there are false negatives, we cannot be sure if they are detected. Like, we don't know if there are any false negatives. But since both tools are more prone to false positives, especially the metadata-based STR, we are more likely to detect more than it actually affects our software. But if there are false negatives, we don't know. It still affects us. So the tool won't solve this problem.
So basically, if the subset that you take from the first analysis into the second analysis, if the second analysis happens to have a false negative, it might discard a vulnerability that wasn't vulnerability.
We actually talk about certain C2P or true positives, not because we cannot tell just by the approach, okay, this is a true positive or this is a false negative. We still need to investigate these vulnerabilities. But to help developers, we say, okay, with the certainty, the vulnerabilities found in the intersection are more likely to be a true positive. So we still should look at every finding, right?
Okay, they're not rule out, they're prioritized.
Yeah.
I get it. Thank you.
Okay.
Hi, I have another question. You mentioned CPEs for identifying software packages. What do you think about package URLs or other ways of identifying those?
There are also tools that uses package URLs or stuff like this, but OWASP Dependency-Check matches on the CPE, so it's the tool implementation. Yeah, but
thanks.
it's also a possibility, right? Okay. So, thank you very much. And I think we are finished. I was very quick.